All right, so now I'm going to very quickly review the elements of differential geometry. And in particular, I'm going to start by talking about manifolds, and their associated tangent spaces. So we've already talked about manifolds before. So I'm going to really focus on sort of what, given a manifold, the associated tangent bundle is. So again, you already have this intuitive notion. It's like what a manifold is. It's some sort of curved object. And it's like if it aids your intuition, it's oftentimes helpful to imagine that it's embedded. It's like into some sort of, it's like embedding or ambient space. And then it's like in the context of that. So in this case, if you imagine you had some sort of curved surface, then the intuition, it's like for what a tangent space at a given point is that it's essentially a linear approximation. It's like of that curved space centered at a given point. All right. So this is a little bit like, for example, having a graph. It's like and then having the tangent. It's like line. It's like to that graph. It's like, but in this case, it would be a tangent plane, right? So associated with any n-dimensional manifold, there is an associated n-dimensional tangent space, if you will. Okay. All right, and then the tangent spaces, it's like to the manifold, are where the tangent vectors live, right? So the tangent space to a manifold at a point, let's call that x on M, right, is denoted by txm, right, and it is a sort of a linear space of the same dimension as the manifold, right? That is sort of the linear approximation of the manifold. Okay, and and the tangent spaces are where the tangent vectors live, right? So the tangent spaces are where tangent vectors live. If you will. Right, so imagine if I have a tangent vector, it's like to a point. So let's say I have an x, so this is maybe v sub x. So one of the things which is going to show up, it's like in sort of discussion of Riemannian geometry, or more sort of generally sort of differential geometry, it's like of manifolds, is this idea that, it's like you're going to have, tangent spaces is like associated at different points on this curved manifold. And one of the things you're going to have to do is to somehow compare them, right? Because if you think about what our usual notion, it's like of taking derivatives is, right? So imagine if you want to take the derivative, so to speak, it's like of a vector valued object, right? Then, I mean, our usual intuition is, so there's another point x prime, so there's a v at this new point, right? The usual notion of taking the derivative, it's like of something, is to take the difference, it's like of the value, it's like of that object, in this case the vector field, at the two different points, and then sort of scale that, divide that by the, it's like the distance between x prime and x, and then look at the limit as the distance between x prime and x goes to 0, right? So that's the usual limit definition, it's like of a derivative. So why is that a problem? Why is that something it's like one has to be a little bit careful about? Well, the reason is, of course, because if you have 2 points on a curved space and you look at this kind of linear space approximations of the curved space, it's like at 2 different points, they don't coincide, right? So this is in contrast to, for example, what happens on a flat space where the tangent spaces have a very, very natural identification of each other. So here it's like when you're in a curved space, you don't have that necessarily. And so, it's like it's not so clear at first glance how do you take the difference of tangent vectors which are based at different points, for example, right? So that's going to require some additional geometric structure. It's like in order to make sense of that, right? So in the context of geometry, it's like differential geometry that sort of goes by the name of an affine connection. So the affine connection gives you some way of sort of comparing it's like tangent spaces at 2 different points, right? And that's an additional structure which you have to add to the system in order to make sense of, it's like the usual time derivatives, it's like which we might want to perform on this. Okay, all right. So anyway, so there's some sort of intuition. It's like that, again, the tangent space at a point is something like the tangent plane. It's like, and you obtain this essentially by sort of a generalization of the Taylor theorem, right? At least if you're in some sort of embedded space or graph, if you will. Okay, so and as I said, it's like the tangent space is a linear space. So one of the things it's like you would want to ask is how do you go about coordinatizing the tangent space, right? So one question which immediately comes to mind is how to coordinatize the tangent space. And so we've already talked about the idea of having coordinate charts. It's like on the manifold itself. So let's just assume that I give you it's like a coordinate chart. It's like on M, which is which contains this point X, and then ask, well, is there a sense in which a coordinate chart it's like on M induces coordinates it's like on the tangent space? So sort of the answer, if you will, is that given the coordinate chart on M, right, we will sort of induce coordinates on TXM. Okay, all right, so let's see what happens. Okay, so again, you have this curved space, you have a point X, right, and you have the tangent space to that. So this is TXM, and you have a manifold, right, and you have some sort of neighborhood. It's like about X, and you have a coordinate chart. Okay, so so if this is a n-dimensional space, it's like you have then a it's like local diffeomorphism. It's like between it's like it's like this neighborhood. It's like of the point X. It's like in M with some neighborhood. It's like some open set. It's like in Rn, right? And you can look at the coordinate lines. It's like in Rn, right? And you can pull it back. It's like to the manifold that gives you coordinate lines on the manifold. Yeah. Okay. So once you have that, in particular, you can have coordinate lines which go to the point X on the manifold, and then you can look at now you have a curve, right? It's like, so you can look at the tangents to those curves, and the claim is that, it's like the tangents to the tangents, it's like to these coordinate lines, the pulled back coordinate lines which you have, then form a basis for the tangent space, okay? So the claim is that given a chart, right, you can consider the coordinate lines m and the tangent vectors to these coordinate lines form a chart. Form a basis for the tangent space. At x, it's like to this manifold, right? Okay, so let's try to look at this a little bit more carefully, right? So if I have a coordinate line associated with the ith component, it's like of this, right? Then sort of this basis vector e sub I, right, which is an element of txm, right, is just defined to be essentially the derivative operator in this direction. Okay, all right. So as it turns out, there are many ways of thinking about tangent vectors. It's like on curved, well, tangent vectors, it's like to curved manifolds. It's like in a way which is intrinsic, right? So right now we've sort of been thinking in the back of our minds, it's like there's some sort of embedding space, it's like which this manifold is embedded in. And in that situation, it sort of makes sense to just think about the usual notion of derivatives, it's like which we have, it's like to talk about the tangent spaces and the tangent vectors and what have you, right? But more generally speaking, it's like you don't have to embed the manifold. You could just say that I give you, it's like a abstract manifold. It's like together with this atlas of coordinate charts, I should still be able to talk about, it's like the tangent space. It's like to that manifold intrinsically, right? So that basically means independent of some sort of embedding. Okay, and so there's sort of two main ways to do this. One of which is to think of, so two main ways of thinking about tangent vectors intrinsically. Okay, so one of which is that you have this manifold M, you have a point X, you have a curve, let's call that, it's like X of t, for lack of better, well, maybe not X of t, it's like, let's call that, it's like R of t, with the property that R at 0 is just X, all right? And then we can consider the equivalence class occurs right, which I denote by sort of this square brackets about R, right? And this is so where we sort of have an equivalence relation which basically says that, okay, so you have R of t, right? And then you have this coordinate chart, okay? So we have an equivalence relation which says that R is equivalent to another curve S, right? If, right, I can, so you have R as a function of t, it's like an S as a function of t, right? So these are curves, it's like on the manifold. I can look at the coordinates associated with that by applying the coordinate chart, right? So I have something like this, and if I differentiate this at time t equals to 0, and I do the same thing for the other piece, right? If these two derivatives, it's like at the level of the coordinate charts, right, are equal, and I can I can make sense of this because if I take r phi and then differentiate, well, if I take r and phi, it's like a t. This is just a curve. It's like in Rn, right, which is parameterized by t. I can differentiate that in the usual way it's like I have with calculus, and evaluate it at t equals 0, and I can do the same thing it's like with the other curve, right? So if those two things it's like have tangents, it's like at the level of the coordinates, right, which are equal to each other, then we say that r is equivalent to s. Okay, so and then this it's like then more or less it's like the set of tangent vectors is like to the it's like to the manifold, right, is given by a family, it's like of curves, right, with the property that all those curves is like go through the initial point x, and so let me take this step back. So for a specific tangent vector, right, to this manifold, right, based at the point x, we associate to this, it's like a family of curves which go through the point x at time 0 and whose derivatives with respect to a given coordinate chart is equal to each other. Okay, and yeah, and sort of is related in some way, shape, or form. It's like to this indexing of the tangent vector. Okay, and I should say that whenever it's like you have these definitions which depend on a choice of chart, you have to be very careful. You have to check that indeed it's like this notion of equivalence is independent of the choice of the chart, and it turns out that it is, right? So if this if this condition holds and you have a second chart, it's like which has the point x as a common point in the domain of definition of the chart, then if this equality holds with respect to one chart, it will hold respect to another chart as well. Okay, so even though I've expressed this notion of equivalence using a given chart, this notion of equivalence is independent of the choice of chart. So it means that this is a well-defined equivalence relationship sort of intrinsically, right? Okay, anyway, so so one way to think about this again is that if you have, it's like a tangent vector, you can associate that to a family of curves, it's like whose first derivatives all agree with each other in some way, shape, or form. Okay, so this way of thinking about tangent vectors is useful for things like what is called the tangent lift. It's like of a map, if you will. So this notion of a tangent vector is useful when sort of considering what are called tangent lifts. So what I mean by that is that imagine you have a map that's like from the manifold to itself, all right? And so you take a point in the manifold, you map it to another point in the manifold. That map induces a mapping at the level of tangent spaces. Okay, so what do I mean by that? So, and if, in fact, it doesn't even have to be a map from the same manifold to itself. So imagine I have a map from one manifold to another manifold. Let's call that f, right? And I have a tangent vector to that, right? And I have a curve. So this is x and this is f of x, right? So the point is that if you have a map from, well, call this something else, m to n, right? So you have f as a map from m to n, right? So in particular, it maps a point x to f of x. Okay, so x gets mapped to f of x. And so the claim is that you can look at its tangent lift at the point x to f, which is going to induce a map from txm to t f of x n in the following way. So a tangent vector, it's like to m, is associated with some sort of curve, right? Equivalence class of curves. Okay. So if you have v sub x can be viewed as this equivalence class, which is an element of the tangent space at x to m. Okay. So I want to sort of find sort of txf applied to vx, right? So this is an equivalence class again. Of curves on n now, okay, centered about f of x. Okay, so you actually sort of do the obvious thing, right? You have some curve, it's like r of t, right, which is a map from some interval I to m, right, with the property that r at 0 is x, and the property that r dot at 0 in some appropriate sense, right, is, let's call that v, right? So I'm just, you know, not going to be very precise here, right? But the idea is that the derivative, it's like of the curve, it's like is going to be identified with this v index, which I have, which is labeling, it's like the vector. Okay, so if you have a map from I to m, I also have a map from m to n, which is f, right? So I can look at this map from I to n by looking at the composition, right? So I can consider the composition f composed with this curve, right? So r, sorry. So this is r, right? F composed of r is now parametrized by t, right? And then this is in n, right? And you can easily check that f composed with r at 0, right, is just f of x, right? So this curve, f composed with r as an equivalence class, right, is an element of the tangent space at fx to n, right? So this is what it's telling you. You have a curve, it's like which is on n. That 0, it's like point of that curve is a base point f of x. So this equivalence class of f composed with r is an element of the tangent space at f of x. It's like to the manifold n. Okay, and right, and you can check what that thing is. It's like, so that vector, it's like here is something like the linearization of f applied to v, if you will. Okay, so that's going to be how that tangent vector transforms. Okay, is you linearize the map, it's like, and then you apply it, it's like to the vector v. Okay, so that makes maybe, yeah, so that maybe it's easier to understand. It's like the map f is a map from the manifold to itself, but you know, this kind of calculation holds more generally. All right, so that's sort of you know, one way of thinking about tangent vectors, right? Is this idea of equivalence classes. But that's not what this notation is sort of screaming out at you, right? I mean, it's like this notation is an alternative way of thinking about tangent vectors, okay? But anyway, so this is one way of thinking about it, and you should be familiar, it's like with both of these definitions, or both these characterizations of tangent spaces to manifolds, at least at an intuitive level, because it's going to help you, you know, it's like understand some of these concepts a little bit better. So the second approach, so the second way of thinking about tangent vectors is by thinking of them as operators, as differential operators. So in particular, sort of directional derivatives. Okay, and you have that these differential operators act on scalar valued functions on the manifold. So which act on scalar valued functions on the manifold. Okay. So, so how do you think about that, right? So if you have a vector field, so given a vector field, sort of given a vector, right, we can consider the directional derivative of a scalar valued function in that direction. All right, and so, all right, so if you imagine, so you first build this by thinking about, well, what are the derivatives? It's like in the coordinate directions, right? So, right, so again, it's like if I have some scalar value function, let's say f, which is a scalar valued function on M, right? And I have the coordinate map phi, which maps M to Rn, and it's like in particular I have coordinates cos C1 to cos Cn, right? Then I can look at f applied to phi applied to a point x, right? And so this gives me f, it's like in terms of cos C1 to cos Cn, right? And then I can differentiate this, and then I can differentiate sort of with respect to the cos Ci's, and that gives me the directional derivative. It's like in each of these generating directions, if you will, right? And then it's like you can, look at the sort of the vector space closure. It's like of those generating sets. It's like by taking linear combinations of this, and then of course you extend the notion of a directional derivative by taking sort of similar linear combinations of these directional derivatives in the basic directions, right? So that gives you a way to take any vector which is spanned, it's like by this basis of tangent vectors in the coordinate directions, right, and identify that with some notion of a directional derivative. It's like for scalar valued functions. Okay, so this turns out to be important. It's like later, it's like when we start talking about curvature, because what's going to happen is that you're going to end up having a sense in which vector fields act on scalar valued functions, and you're going to start talking about, it's like applying sort of more than one tangent vector, or more than one vector field. It's like to the same scalar valued function, and so this, for example, is going to be relevant. It's like in measuring to the extent to which various things commute. So things like the Jacobi-Lie bracket of vector fields, right? It's going to be defined. It's like with this idea of thinking of tangent vectors and more generally vector fields as differential operators associated with directional derivatives. So yeah, so anyway, it's like, so these are, it's like, so this idea of equivalence classes of curves, right, where the linearization of the curve agrees with each other. If that's true, then you identify those curves. And this other idea of thinking of tangent vectors as directional derivatives, those are sort of the two main ways, it's like, by which you think about tangent spaces to manifolds in a way which is intrinsic and which doesn't rely, it's like, on the choice of an embedding. It only relies, it's like, on the stuff which is given to you, which is an atlas of coordinate charts. Okay. All right. So and yeah, so let me just stop here for now. It's like, and then we'll talk about given this notion of tangent spaces, how you build additional structure in it. In particular, how do you start measuring the length of tangent vectors through something like a Riemannian metric? So let me just stop here for now.